Hi students, welcome to the next chapter from your second year physics. So far you have learned about electrical field and electrical field intensity, electric charge, electric field intensity, electrical potential and capacitance. This all together generally call it as electrostatics, but it consists of two chapters. So that is over. Also current electricity, there also you are learning something about a charge, something about circuits also. So what is the difference between first two chapters and the third chapter, which means electric field, electric charge, electrical potential and capacitance with current electricity. Current electricity is your third chapter. There, what is the difference between compared to the first chapter and the second chapter? In the first chapter, you are learning about the charges. Charges are at rest. Charges are not moving in the first two chapters. But in the third chapters, the charges are flowing and the flow of charge is called current. That's what you have learned in current electricity. So flow of charge will give rise to current. So first two chapters you have learned about charge is static, charge is not moving within a conductor, charge is not moving. So such a scenario we have learned first two chapters. Come to current electricity, you are learning what will happen if a charge is moving. If a charge is started to flow, charge is started to move, then it is called current. So you are learning the dynamic effect of charges. Dynamic means motion. The motion effect of the charges that you have learned in your third chapter of current electricity. Now I am going to take the fourth chapter in the Ncert textbook, which is called magnetic effect of current. Okay, magnetic effect of current, you can from the word itself you know. So first one is charge. Charge is at rest, that is called electric field, electric charge, electrical potential and capacitance. So the electrical effect of charge, which is called electric current, right? That is your third chapter, which is another way we named it as current electricity. Charges is moving. So the effect of charge we are learning in current electricity third chapter. Now we are going to learn effect of charge will give rise to an current and effect of current will give rise to magnetism. So that's what we are going to learn in the fourth chapter. So this is just like a chain connections between, right? These first four chapters are pretty much connected between each others. First one is a charge at rest. In come to current electricity, charges are started to flowing. When come to magnetic effect of current, in third chapters we have learned about the flow of charge will give rise to current. In fourth chapter we are give rise to what will happen if current will be there. If current will be there, magnetism will be there. Magnetic effects will be there. So it is just connected. So without wasting the times, we will jump into this pool of this magnetism. Of course, in small classes and schools days onwards, very small school days onwards, we are learning much about, we have hearing the word called magnetism, right? We know what is magnet. Okay, we know magnet, it is a kind of force or it's a kind of strength. So the same things we are learning, but here we are going to learn about electromagnet, which means a current can produce a magnetism. Okay, that is a whole idea behind these chapters. So we will move forward and to see what are the things are included in this chapter. So you can write the heading magnetic effect of current. Magnetic effect of current. Okay, this is your NCERT textbook, fourth chapter, magnetic effect of current. Okay, NCERT fourth chapter, you have to learn, definitely you have to read NCERT textbook after attending my classes. You have to learn from me something and then you go and read your NCERT textbook. Similarly for all the chapters, whatever we have completed. Now we are at the fourth chapter. So what is this gave rise to? Magnetic effects of current. Current will give rise to magnetism. So you can write on the first heading called Ncert's experiment. Ncert's experiment. This is not important for Neet or as well as for JE, not at all important, but it's a concept, it's a very fundamentals. What is an Ncert's experiment is saying like that. Suppose I have a current carrying conductor, current is carrying in the direction. I have placed a magnetic compass will be here. Magnetic compass is a device that is used to get the direction of the magnetic field. So if a magnetic compass is placed will be here, its needle, this is the 0th position, you can assume the needle is deflected towards this side. But if I am changing the direction of the current in a conductor, the magnetocompass needle will be deflected in another direction. This is a 0 axis. Okay. So which means that when the current direction changes, the direction of the magnetic field also changes. So magnetic compass is used to detect the presence of magnetic field. The presence of magnetic field. So magnetic compass is a device used to detect the presence of magnetic field. And the next point, when current direction changes, you can write these points. When direction of current changes or current direction changes, when direction of the current changes, direction of what will changes? Direction of magnetic field also changes. Direction of magnetic field also changes. Okay, that is the points behind will be here. So magnetic compass is a device which is used to detect the presence of magnetic field. Whenever the direction of the current changes, direction of the magnetic field will also changes. Magnetic field is representing using a letter called B. As this is a vector quantity, we can mark it as an arrow mark on top of this one. This is called Ncert's experiment. Hope it is clear to you. Next, we are moving to the next topic. And next topic is called Biot-Savart's law. Biot-Savart's law. B-I-O-T. Biot-Savart's law. Okay. So what is called Biot-Savart's law? Biot-Savart's law is a law which is related to to find out the magnetic field intensity. Okay. Normally for board examination perspective, there are some 5 marks, 10 mark questions will come from this session, sir. But in entrance perspective, again it is Paka conceptual oriented. Let's take a current going in a current element DL. DL is the current element. This is a long length and DL is the length of this piece. This small piece will be here called DL. I am going to find out magnetic field at the point B, which is at a distance of r meter away, and the angle is called theta. Okay, so the magnetic field at this point P is equal to, okay, what this is saying like that, magnetic field is directly proportional to product of the current element IDL is directly proportional to product of the current element. If you are written I and DL, I is called current, DL is called element. So it's called ideal. Magnetic field is directly proportional to current element. Magnetic field is inversely proportional to square of the distance between them. And magnetic field is directly proportional to sine of angle between IDL and R vector. So magnetic field is directly proportional to IDL, current element. Magnetic field is directly proportional to 1 by R square, square of the distance between the current element and the point where I am measuring the magnetic field. And magnetic field is directly proportional to sine theta, where theta is the angle between the current element and the vector called R. Okay, this is what is this law states that. This law will be given 3 statements. By comparing these 3 statements, I can written as B is proportional to IDL sine theta divided by R square. So which means the proportionality constant. Proportionality is replaced with a constant. That constant in magnetism, in electrostatics, in electric charge, electric field, Coulomb's law, we call it as, what we call it as? Permittivity. Here we call some other term called permeability. Mu 0 by 4 pi into IDL sine theta divided by R square. Okay, this I would like to call this as scalar form. I like to call it as scalar form. So this is a scalar form of Biot-Savart's law. B is equal to mu 0 by 4 pi into IDL sine theta by r square. What is mu 0? Mu 0 is called permeability. Mu 0 is called permeability. Mu 0 is called permeability of air, or also it is called free space. Both are same. That's what mu 0 is coming. Okay, then the value of mu 0 divided by 4 pi is equal to 10 power minus 7. Remember these things. So I'll repeat, Biot-Savart's law states that magnetic field produced by a current carrying conductor. Who told that law? Ncert's experiment states that when a current is passing through a coil, a wire, magnetic field will produce us. Because of that one, the magnetic needle is rotating towards left. Whenever the current direction changes, the magnetic needle will towards right. So which means current is going upward or downward, whatever it is, magnetic field is producing. But the magnetic compass is rotating in different direction. So which means that magnetic field is a vector quantity. This is a vector quantity. Okay, that is an additional point I am saying. B is a vector quantity. B is a vector quantity, magnetic field. Because the compass depends upon the direction of the current, the magnetic needle is also rotating in the different directions. Okay. Next one is Biot-Savart's law. Biot-Savart's law is just a continuation of Ncert's experiment, where it is stated sorry. Okay, what it states that Biot-Savart's law states that whenever the current is passing through a current element I and dl, the distance between the current element and the distance is called r. So B is proportional to IDL and B is proportional to 1 by r square and B is proportional to sine theta. By combining all this one, B is equal to mu 0 by 4 pi IDL sine theta by r square. This is a scalar form. And mu 0 is called permeability of air in a free space. Air is also called free space. Mu 0 by 4 pi, the value is 10 power minus 7. Mu 0 is called permeability. Again, it is called something related to something similar to epsilon 0. Epsilon 0 is called permittivity. How much a medium can permit electric field. Permittivity is the ability of a medium to permit electric field. Permeability is the ability of a medium to permit magnetic field. Okay, epsilon 0 in electric charges in Coulomb's law, and here when comes will be here in Biot-Savart's law, it's called permeability. Both are one and the same, but one is the permittivity of a medium to allow what called electric field intensity. Here permeability, it's actually a permittivity of a medium to allow magnetic field, that is called permeability. Okay, so now we will dig into a little bit of concepts from Biot-Savart's law. This is not enough to explain Biot-Savart's law. Entrance point of view, we have to little bit dig into the area. Okay, so this is a very fundamental stuffs we have learned, and we will see what all the things will be there associated with this one. Next one, you can write specific heading, vector form of Biot-Savart's law. Vector form of Biot-Savart's law. Okay, what is vector form of Biot-Savart's law? Listen very carefully. Vector B is equal to mu 0 by 4 pi is a constant I into dl cross r divided by r cube, dl cross by r cube. This is important. Okay, this is a vector form of Biot-Savart's law. Mu 0 by 4 pi I into dl cross r. dl cross r. So here, once you look into the vector form, how many arrow marks will be there on the right hand side? There are two arrow marks will be there. dl on top of dl one arrow mark, on top of r another arrow mark, and B will have left side only one arrow mark. So which means the direction of the magnetic field is the resultant of the direction of dl and r. So direction is important. That's what we are learning about the vector form. So the first point is direction of B is the resultant direction of direction of dl and r. Okay, so direction of B is the resultant of dl and r. How to find out the cross product of two vectors? So here dl, how I can find the resultant of dl and r? For that I will going little bit into your first year physics vector rule. Okay, little bit fundamental is required. Suppose I have a vector called, okay, let me take it like this example. I have one vector. Okay, let me start from here. Vector A cross B is equal to vector C. Now you are asking what is the direction of C? So now I am applying vector A is in this direction and vector A in the direction and vector B in the direction. Then I am asking you, what is the direction of vector C? Can anybody answer this question in your mind? Because you have learned this on your first year. If you are answering, at least I can say your fundamentals in vector is very clear. Otherwise it's not clear. Okay, because this is a very fundamental, like how we will do like mathematical additions, right, in physics, in maths. So say this is very fundamentals of vector. I have one vector like this, I have another vector like this. How I can find the resultant of this vector? This is like, for this one we will use right hand rule. Simply I can say right hand. Okay, right hand thumb rule. Right hand thumb rule. I can use right hand thumb rule. There is something called screw rule also will be here, screw rule, but I'll prefer to do this one because it's quite easy for me. I hope this will be easy for you also. Right hand thumb rule means what? Right hand thumb rule means in the direction of A. Okay, if you are not remembering the law, just listen here. If A is the first vector, so you have to use your right hand. So right hand palm you have to place it like this one. Then B is in this direction going upward. So A is placed like this one. Then what the direction B is there, in the same direction you have to fold it, your other fingers. So your thumb is pointing outside direction, outside. Okay. So outside means the direction of C is outside. I can say outside, or I can say out of board in my case. In my case it is out of board. Out of board. So right hand thumb rule is used to find out the direction of the cross product of two vectors. Right hand thumb rule is used to find out the direction of the cross product. Simply we call it as right hand rule also. Some reference book it can also say that right hand thumb, because thumb is giving the direction of the final vector. So vector A cross B. B means you have to fold in this direction, upside. Okay, then you will get your thumb is pointing towards you. Okay, so A cross B will give rise to DL. So in this case, DL cross R will give rise to B. Now we look back to this one. This is a diagram we have drawn. We have drawn like a current direction is same as current is going in upside direction. So the DL direction is also in the direction of the current. In the direction of the current. So DL is going in the upside directions. So DL is going in the upside direction, which means current is also going in the upside directions. So DL is upside. So we will just mark this is our DL vector, DL and cross R. R is in this directions. Okay, R in the direction. Now you have to use your right hand. So first DL is in this direction and R is what direction? R is in this direction, right? So R is a vector which is pointing in this direction. R is pointing in this direction. So right hand you have to use, and what direction it is pointing? It is pointing in this direction. So your magnetic field is outside. Okay, you have to use your, not use your left side. I used my left side, sorry for that. We have to use our right side. So DL is upside and the R vector is in this direction. Correct? So this DL So DL cross R, so you have to just tilt it. So what you can see, your thumb is going inside. So here I can say, in this concept, based on the diagram, here magnetic field is inside. Magnetic field is inside, or I can say it is into the board, or I can say it's into the board. Hope this is clear to you. So magnetic field is inside the board using the right hand thumb rule, because if you know the direction of DL, you keep your hand like this one in the direction of DL, palm. Okay, so palm is in the direction, then I have to turn towards the direction of R. So my thumb is going into the board. So at this point, the magnetic field is inside the board, because the magnetic field direction is given by your thumb. Okay, so right hand thumb rule, we will write it on. Okay, so okay, hope you understood the concepts. Now we are learning this stuffs, we are writing the notes. So the vector form of Biot-Savart's law, it's there in the board, you have to note down. So to find out the direction of the two vectors, we are using the right hand thumb rule. So what is this right hand thumb rule? We will write a note, right hand thumb rule. Right hand thumb rule states that palm represent first vector, in this case vector A, and other four curling fingers, curling means rotating, other four, F-O-U-R, other four curling fingers other four curling fingers represent the direction of vector B. Other four curling fingers representing the direction of B. Direction of B. Then in this case, the thumb represent the direction of vector C. In bracket you can write resultant of vector A and vector B. The direction of resultant of A and B. Hope it is clear. Right hand thumb rule states that the first vector is representing the direction of first vector A, representing the palm represent the first vector, other four curling fingers represent the direction of B, then the thumb represent the direction of the vector C, which is a resultant of A and B. So DL cross R in this diagram, this is our DL direction and this is our R directions, and we are calculating the magnetic field at this point. So here palm is, so in this example you can draw somewhere and you can represent palm is pointing upward, and four fingers, F-O-U-R, four fingers in what direction? Four fingers in R direction, in R. Okay, then thumb gives vector B. Okay, here I have written palm is pointing upward, palm DL vector, and four fingers, other four fingers are in direction. Then your thumb gives, so right hand DL cross R, so DL direction you keep it your hand, then cross R direction you are folding your four fingers, then the vector is going towards inside the board. So DL cross R will give rise to the magnetic field intensity direction. This is called right hand palm rule. So from the right hand palm rule you can apply to DL cross R and you will get the direction of magnetic field intensity. Not right hand palm rule, right hand thumb rule. Right hand palm rule is different, that is yet to come. So right hand thumb rule, hope you understood. Okay, now we are moving to learn about the next theory, and which is called, now we have learned about something called right hand thumb rule, right? This right hand thumb rule you are learning from your I can say from your first year physics onwards. And here we are going to learn one more rule with respect to right hand, and that is called right hand palm rule. So you can write out the heading called right hand palm rule. Okay, so right hand palm rule. Right hand palm rule. What is the right hand palm rule represent means? What you have not right hand palm rule, this is also called right hand thumb rule, or palm, not right hand thumb rule. This is also another, okay, right hand thumb rule, both are same. Okay, right hand thumb rule. So right hand thumb rule, or this is also called right hand rule. So right hand thumb rule can be defined it in another way. Okay, defined another way means if you have vector A and vector B will be there, A cross B is equal to C. We know how to find out. Right hand will placed, other four fingers are folding in the direction of the second vector. So your thumb is either pointing inside, outside, or any other direction. That is the direction of magnetic field intensity. And here also right hand thumb rule, the another way of representing the direction of the right hand thumb rule. What it's indicate like is that, and here the direction of thumb represent, here the direction of thumb represent the direction of current. Right hand thumb represent the direction of the current. Then other four curling fingers representing the direction of magnetic field, in bracket B, vector B. What it says that here direction of thumb represent the direction of the current, thumb represent. Then the other four curling fingers represent the direction of magnetic field. Okay, so let's take an example in our previous cases. In our Biot Savart law, we have considered a current element I. So dl is also in the directions, and r at a distance. Here we need to find out magnetic field based on dl cross r concept. So this is like a dl. This element is called a dl. This a current element is called a dl. So this dl cross r concepts, we told dl is in this direction, dl cross r is going towards right. So my magnetic field is inside. Right hand thumb rule. First year physics, a very basic fundamentals theorem you can apply for any role. But here in this case, this is exclusive to magnetic field intensity because it is with respect to current. So what is the direction of the current is pointing? Now the direction of the current is going topward. So what you have to do means, you have to point your thumb in the direction. Then you have to rotate your all other four fingers, you rotate like this one. So thumb is pointing towards upside. If thumb is pointing towards upside, if you rotate all other four curling fingers, if thumb is pointing towards upside, if you rotate other four curling fingers, means you can see right side my fingers are going into the board. So this is, you can assume this is a pen, and in the upside direction the current is going. Now I am keeping my thumb in the direction of current and I am rotating. So right side my fingers are going inside and left side it is coming outside. So my four fingers are going inside at the point P, and this side it is coming out. It's rotating like this, right? These four fingers are rotating. My thumb is fixed. Thumb direction is fixed, but four fingers are rotating. So based on this one, the magnetic field is inside at the point P. Okay, this is another way of find out the direction of the magnetic field from direction of current. Okay, so in short I am writing direction of B can be find, this is important, can be find from, here I have written a statement, direction of B can be found from the direction of I. I is not a scalar quantity actually. I is not a vector quantity. It is a mix of scalar and vector quantity, and that is called tensor quantities. Current is not a scalar, current is not a vector, it is called a tensor quantity. That is not there in the syllabus, but just understand it's neither a vector nor a scalar quantity. But in your syllabus you have to learn only two things. If every rules are obeyed by a certain quantity, then it is called vector. If some rules are violating by some vector, then it is called scalar. So in your chapter you are considering current is a scalar quantity, but if you are going for higher studies you will learn about this is called a tensor quantity. Tensor, T-E-N-S-O-R. I will just write it. It's not there in the syllabus, you don't want to remember it at all. If you are going for higher studies, this is required. Okay, but at the moment this is like for your case it's not obeying all the rules of vector, so it is considered as a scalar quantity in your cases. That's what I have not taken any arrow mark on top of I, but I have placed arrow mark on top of B because B is a purely vector quantity. So direction of B from direction of current can be found using right hand thumb rule. Okay, hope these two concepts are clear. We'll move ahead. Okay, fine, good. So what are the things we have learned? Just a reminder. Okay, Ncert experiment. The current from the direction of the current, a current carrying coil will be produce a magnetic field. Then we have learned about Biot-Savart's law, ideal sine theta by r square in scalar format, mu 0 by 4 pi into I into dl cross r divided by r cube is the vector format. And the direction of the magnetic field can be found out using right hand thumb rule. There are two methods will be there, either palm with the 4 curling fingers and thumb is representing the direction of the magnetic field, or another way from the direction of the current. So dl from the direction of with the help of dl and r I can able to find out the direction of magnetic field, or in another way without a dl and r only with the help of current also I can able to find the direction of magnetic field. Direction of the magnetic field can be easily find out from the direction of the current by using right hand thumb rule. For that the thumb is representing the direction of the current and your all other 4 curling fingers representing the direction of magnetic field intensity. Okay, hope this is clear to you. Now we are entering the next major topic, and this is quite important for entrance examination. Application of Biot-Savart's law. Application of Biot-Savart's law. Application of Biot-Savart's law. So what is this indicates us to us? Application of Biot-Savart's law means what this is indicating to us. We are applying Biot-Savart's law in order to find certain things. Okay, so the application of Biot-Savart's law, the first one is magnetic field B due to a finite current carrying conductor, a finite current carrying conductor, a finite current carrying conductor. Magnetic field due to a finite current carrying conductor. Okay, this is what we are going to do. Magnetic field due to a finite current carrying conductor. Okay, what all the things we are going to apply will be here. Magnetic field due to a finite current carrying conductor. Let's assume I have a current carrying conductor from this end. Finite means fixed end. I am going to find out magnetic field at a distance of r meter. Okay, let me put it as small a because another r is coming, so it will not be get confused. So this at a center point, and these two edges are marked with the phi 1 angle, and this is marked with phi 2. This is a point where I am going to find out magnetic field intensity. So to know that this is a current element and which is carrying the current of IA, this is our current element. So what we are going to do means I am taking one small piece will be here, and this small piece will have a length called dl, and the full length we have, of course we have L will be here. Okay, and this small angle I am considering as theta, and the distance from here to here it is called r. So I need to find out the magnetic field for this full conductor. Okay, So let's apply. So magnetic field B is equal to mu 0 by 4 pi. Okay. Ideal sine theta. We are going to find out the magnitude format. Vector format we don't want to find out. Vector format means we'll get direction also. Mu 0 by 4 pi into ideal sine theta divided by r square. Okay. This is a general format. Now we will see each of the term will replace mu 0 by 4 pi. I is same. dl. Okay. What is called dl from the diagram? dl is the thing in which I have assumed. It's not given will be there. What is called dl from here? We'll find some other quantities will be here. What is called dl? If you take a tan theta is equal to what? Opposite side by adjacent side. So dl divided by a. So dl I can written as a tan theta. Okay, dl I can take an or instead we will do one thing. This will be considered as an element called L. Okay, so this will be considered as an L which a distance of r meter. Okay, this is a full conductor we can assume. We don't know the size, but we know only it is called a finite conductor. So let's consider this as L. So tan theta will be equal to L by A. So L will be equal to A tan theta. I can written like this one, right? Now we need to get here as per the formula we need to get dl. So what is dl from here? dl will be equal to A into sec square theta. Differentiation of tan theta is sec square theta. So I into A into sec square theta supplying will be here. Okay, so I into a sec square theta. Next one is sine theta. Here while we are representing the Biot-Savart's law, I told theta is the angle between ideal and r. So this is called the current element. IL is a current element, and with respect to this angle is called theta. Okay, this is not theta will be here. Why? Because this angle is theta and this is 90. So what this will come? 90 minus theta. So here I have to apply sine of 90 minus theta, because the direction of the current and r, that angle is called theta will be here. But here it is not theta. Here theta is assumed this angle. So this become 90 minus theta divided by r square. So r is the parameter also I have assumed. Only given thing in the question is phi 1, phi 2 and a. So r I have to replace. So what is called r? Let me take cos theta. So what is cos theta? Adjacent side a divided by r. So r is equal to a by cos theta. So r is equal to a by cos theta means a square by cos square theta. Okay, so let's move to the further steps will be here. Mu 0 by 4 pi, mu 0 by 4 pi, I into a into sec square theta. Sec square theta, sine of 90 minus theta cos theta multiplied with cos square theta will go to numerator divided by a square. Divided by a square. So a and a will get cancelled. So mu 0 I divided by 4 pi. This is called, this is not called B, this is called dB, a small magnetic field. Because we need to find out the full magnetic field. So this is something called a dB, a small magnetic field. So mu 0 by I into a into sec square. Okay, sec square theta written as 1 by cos square theta. So this will be cancelled. So it become cos theta divided by a. This is nothing but called dB. What we need to get? dB is a magnetic field produced by this much length of conductor. But I need the magnetic field produced by from here to here. For that what I need to do? I have a small magnetic field. I need to integrate over a range. So this is what I am going to do. I'll use this space for the same. Okay, I am doing the integrations. So far you can pause the video and you can complete the notebooks. So here we have the diagrams also will be there. And we are applying. So integral dB is equal to integral mu 0 I cos theta divided by 4 pi a. Okay. L is equal to A tan theta. DL equal to A sec square theta d theta. So one d theta will be here extra. So d theta and d theta. So left side we are differentiating b. Here it is small db. Now here if you integrate you will get full db. So here d theta is there extra. I missed to write d theta will be here. So please write d theta. So integration limit is a full db, so it become b. What is the integration limit of theta? Theta is varied from phi1 to phi2. Okay, so with respect to the central axis, this is symmetrical structure. So the lower limit is minus phi2 and upper one is plus phi1. If you have anything similar to the like the symmetrical bottom and right, in electrostatics also we have taken the same sign conventions. If it is a symmetrical structure, the one come below is called negative, one come above is called positive. So minus phi2 to phi1 mu 0 I 4 pi a into cos theta d theta. These all things are constant. We can take it outside. So b is equal to mu 0 I divided by 4 pi a. What is the integral of cos theta? It is called minus sin theta and integration limit minus phi 2 to phi 1. So we are further writing mu 0 I divided by 4 pi a into this minus is taken outside. So sin phi 1 minus sin of minus phi 2. Okay. Now we'll say. Okay. So mu 0 I divided by 4 pi a minus will be here. Sin phi 1 minus minus become plus sin of phi 2. Okay. So this minus is taken outside. So sin phi 1 minus sin of minus phi 2. So sin is an odd function. So this minus will come outside. So it become sin phi 1 plus sin phi 2 and mu 0 divided by 4 pi a. So mu 0 divided by 4 pi a into sin phi 1 minus sin phi 2. Here one mistakes will be done, right? Cos theta integral is plus sin theta. Sin theta integral is cos theta. So it become plus. So this become plus. Okay. So sin mu 0 by I into cos theta integral. Okay. Integral of cos theta. It is called what? Sin theta. Integral of sin theta, which is called minus cos theta. So if you have confused, you write just write down. So minus sin theta. So sin phi 1 minus sin phi 2. Sin is an odd function. So sin of minus theta. This also you can write if you don't know. Sin of minus theta equal to minus sin theta. Cos of minus theta equal to cos theta. So cos is called an odd function. Sin is called cos is called an even function. Cos of minus theta equal to cos theta. Sin of minus theta equal to minus sin theta. So this minus will come outside. So it become plus. So this is the magnetic field intensity due to a finite current carrying conductor. Mu 0 by I into 4 pi a into sin of phi 1 plus sin of phi 2. Okay. So remember this derivations part. This is a large conductor and whose length is taken as capital L. And we have considered like a small L will be here. And we have started to do the derivations and we are replacing in Biot-Savart's law 1 by 1 term mu 0 by ideal sin theta divided by r square. Insert theta will be here means 90 minus theta. The question is given, the original pictures will have phi 1 will be there and phi 2 will be there and small letter a will be there. So our answer should also containing only that terms what is given in the question, phi 1, phi 2 and a. So you can see phi 1, phi 2 and a and current will be there. But all these things like theta, small letter r, small letter l, these all the things I have assumed, I have taken in order to apply Biot-Savart's law. So this is my assumptions only. Theta 90 minus theta RL, these are the things extra we are introduced to get the final formula. So these parameters should not be there in the final equation. Your final equations only contains phi 1, phi 2 and IA. Okay. So hope this derivation is clear. This formula is important. Mu 0 by I into 4 pi a into sine of phi 1 plus sine of phi 2. This is a magnetic field due to a finite current carrying conductor. Finite means fixed length.